Hello and welcome. In this video, we'll be diving into the world of exponents and logarithms, a fundamental topic in IB AHL mathematics. By the end of this session, you will be able to apply the laws of exponents to simplify complex expressions, solve exponential equations by finding a common base, and understand the relationship between exponents and logarithms. We'll start by revisiting the core rules of exponents, which are essential for everything that follows. Then, we'll see how these rules help us solve equations where the unknown is in the exponent. Finally, we'll introduce the concept of a logarithm as the inverse operation to exponentiation. Let's begin with the basics. An exponent is a shorthand way of writing repeated multiplication. A number written in exponent form looks like this: a to the power of n. Here, a is called the base, and n is the exponent or power. It tells us to multiply the base, a, by itself, n, times. For example, 2 to the power of 3, or 2 cubed, means 2 times 2 times 2, which equals 8. So 2 cubed is 8. The base is 2, and the exponent is 3. Now, let's explore the fundamental rules, or laws, of exponents. These rules are incredibly powerful for simplifying expressions. Our first law deals with multiplying powers with the same base. The rule states that when you multiply two powers with the same base, you add their exponents. So, a to the m times a to the n equals a to the power of m plus n. Let's see why this works with an example. Consider a cubed times a to the fourth. A cubed is a times a times a to the fourth is a times a times a times a. When we multiply them together, we have a total of 7 a's being multiplied. This is the same as a to the power of 3 plus 4, which is a to the 7th. Let's try another one. Simplify 5 to the power of 7 times 5 to the power of negative 2. Using our rule, we add the exponents. 7 plus negative 2. This gives us 5 to the power of 5. This rule is a cornerstone of exponent manipulation. Remember, you can only use it when the bases are identical. Next, let's look at dividing powers with the same base. The rule for division is that you subtract the exponents. So a to the m divided by a to the n equals a to the power of m minus n. Let's use our previous example. A cubed divided by a to the fourth. We can write this as a fraction. We have 3 a's on top and 4 on the bottom. 3 of them cancel out, leaving us with 1 over a. Using our rule, we get a to the power of 3 minus 4, which is a to the negative 1. This shows us that a to the negative 1 is the same as 1 over a. This leads to a very important definition. A negative exponent means you take the reciprocal of the base raised to the positive exponent. So a to the negative n is equal to 1 over a to the n. This is a crucial concept for simplifying expressions. Let's try another example. Simplify x to the power of 8 divided by x to the power of negative 3. We subtract the exponents, 8 minus negative 3. Remember that subtracting a negative is the same as adding a positive, so we get x to the power of 11. Our third law deals with a power raised to another power. The rule states that when you raise a power to another power, you multiply the exponents. So a to the m, all to the power of n, equals a to the power of m times n. Let's see this in action. Consider a to the fourth, all cubed. This means we multiply a to the fourth by itself 3 times. Using our first law, we add the exponents, 4 plus 4 plus 4, which is 12. This is the same as multiplying the exponents. 4 times 3 is 12. So the result is a to the 12th. This law is also the key to understanding fractional exponents. A fractional exponent like 1 over n represents the nth root. For example, a to the power of 1/2 is the square root of and a to the power of 1/3 is the cube root of Let's evaluate 64 to the power of 2/3. We can rewrite this as 64 to the power of 1/3 all squared. The cube root of 64 is 4, because 4 times 4 times 4 is 64. Then we square 4 to get 16. So 64 to the power of 2/3 is 16. So far, we focused on expressions with the same base. But what if the bases are different? There are two more laws that apply when the bases are different but the exponents are the same. The first rule states that a to the n times b to the n is equal to the product of the bases, a times b, all to the power of n. Let's see why. Consider 3 squared times 5 squared. This is 3 times 3 times 5 times 5. We can rearrange the terms to get 3 times 5 times 3 times 5. This is 15 times 15, which is 15 squared. So 3 squared times 5 squared equals 15 squared. The second rule is similar for division. A to the n divided by b to the n is equal to the quotient of the bases, a divided by b, all to the power of n. Let's use this to simplify 6 cubed divided by 2 cubed. We can write this as 6 divided by 2, all cubed. 6 divided by 2 is 3, and 3 cubed is 27. This is much simpler than calculating 6 cubed and 2 cubed separately. Now that we've reviewed the laws, let's tackle some more complex simplification problems. These often involve combining multiple rules. Our goal is to write the final answer without brackets or negative exponents. Let's simplify the expression, the quantity 3a cubed, all to the 4th power divided by 9a squared. First, we'll apply the power rule to the numerator. The exponent 4 applies to both the 3 and the a cubed. So we get 3 to the 4th times a to the power of 3 times 4, which is a to the 12th. 3 to the 4th is 81, so the numerator becomes 81 a to the 12th. Now let's substitute this back into our expression. We have 81 a to the 12th divided by 9a squared. We can simplify the coefficients and the variables separately. 81 divided by 9 is 9. For the variables, we use the division rule and subtract the exponents. A to the 12th divided by a squared is a to the power of 12 minus 2, which is a to the 10th. So our final simplified expression is 9 a to the 10th. Let's try another one, this time involving negative and fractional exponents. We need to simplify the quantity 27x to the 9th divided by 64, all to the power of negative 1/3. The first thing we should do is deal with the negative exponent. Remember, a negative exponent means we take the reciprocal of the base. So we flip the fraction inside the brackets and change the exponent to positive 1/3. This gives us 64 divided by 27x to the 9th, all to the power of 1/3. Now, the exponent 1/3 applies to every term inside the brackets. This means we need to find the cube root of 64, the cube root of 27, and the cube root of x to the 9th. Let's calculate each part. The cube root of 64 is 4. The cube root of 27 is 3. And for x to the 9th, we multiply the exponents. 9 times 1/3 is 3. So the cube root of 27x to the 9th is 3x cubed. Putting it all together, our simplified expression is 4 divided by 3x cubed. Now let's move on to solving equations. Our goal here is to find the value of an unknown variable, often x. A common strategy for solving exponential equations is to rewrite both sides of the equation with the same base. Let's solve the equation 8 to the power of x equals 32. We need to find a common base for 8 and 32. Both are powers of 2. We know that 8 is 2 cubed and 32 is 2 to the 5th power. Now we can substitute these into our original equation. This gives us 2 cubed all to the power of x equals 2 to the 5th. Using the power rule on the left side, we multiply the exponents. This simplifies to 2 to the power of 3x equals 2 to the 5th. Now since the bases are the same, the exponents must also be equal. This is a key property of exponential functions. So we can set the exponents equal to each other. 3x equals 5. Solving for x, we find that x equals 5/3. Let's try a more complex equation that requires a bit more manipulation. Solve for x4 to the power of 1.5 equals 2 times 16 to the power of x minus 1. Again, our strategy is to find a common base. In this case, the base 2 seems like a good choice. We know that 4 is 2 squared, and 16 is 2 to the 4th. Let's substitute these into the equation. The left side becomes 2 squared, all to the power of 1.5x. The right side becomes 2 times 2 to the fourth, all to the power of x minus 1. Now we simplify both sides using the power rule. On the left, 2 times 1.5x is 3x. On the right, 4 times x1 is 4x minus 4. So we have 2 to the 3x equals 2 times 2 to the 4 x minus 4. The right side is a product of powers with the same base. We can simplify it by adding the exponents. Remember that 2 is the same as 2 to the power of 1. So we add 1 to the exponent, 4x minus 4, which gives us 4x minus 3. Our equation is now 2 to the 3x equals 2 to the 4x minus 3. Since the bases are the same, we can equate the exponents. We have 3x equals 4x minus 3. Subtracting 3x from both sides gives us 0 equals x minus 3. Adding 3 to both sides, we find that x equals 3. Let's look at one more type of equation, where the variable appears in multiple terms. Solve for x 16 plus 2 to the power of x equals 2 to the power of x plus 1. The key here is to use the exponent laws to separate the terms with x. We can rewrite 2 to the power of x plus 1 as 2 to the x times 2 to the 1. This is just the product rule in reverse. Now let's substitute this back into our equation. We have 16 plus 2 to the x equals 2 times 2 to the x. Notice that we have the term 2 to the x on both sides. This suggests we can treat it like a single variable. Let's move all the 2 to the x terms to one side. Subtracting 2 to the x from both sides gives us 16 equals 2 times 2 to the x minus 2 to the x. On the right side, we have 2 of something minus 1 of that same something. This leaves us with 1 of that something. So 16 equals 2 to the x. Now we just need to find what power of 2 gives 16. We know that 2 to the fourth is 16. Therefore, x equals 4. We've seen how to solve equations by finding a common base. But what if we can't easily do that? For example, how would you solve 2 to the x equals 7? This is where logarithms come in. A logarithm is simply the inverse operation of exponentiation. The statement, a to the power of x equals b, is equivalent to the statement log base a of b equals x. Let's break this down. The logarithm, written as log, asks a question. To what power must we raise the base, a, to get the number b? The answer to that question is x. So to solve our problem, 2 to the x equals 7, we can rewrite it in logarithmic form. The base is 2, the number is 7, and the exponent is x. So x equals log base 2 of 7. This is the exact solution. We can use a calculator to find its approximate value, which is about 2.81. This shows the fundamental relationship between exponents and logarithms. They are two different ways of expressing the same mathematical idea. Let's recap what we've covered today. We started by reviewing the 5 key laws of exponents. These laws are essential tools for simplifying expressions and solving equations. Remember, they are not in your formula booklet, so you must know them. We then applied these laws to solve exponential equations by finding a common base. This powerful technique allows us to turn an exponential equation into a simpler algebraic one. Finally, we introduced the concept of a logarithm as the inverse of an exponent, providing a way to solve equations where a common base isn't obvious. This fundamental relationship will be the basis for our next topics, where we'll explore the properties and graphs of logarithms in more detail. To solidify your understanding, here are 5 practice questions. I encourage you to pause the video and work through them on your own. Thank you for watching. I hope this video has helped you build a strong foundation in exponents and logarithms. Keep practicing, and I'll see you in the next one.